Welcome to this video. Here we show that the determinant function is multiplicative. We prove this by first showing that there is a way to calculate determinants uniquely, and that any given n-linear alternating function can also be calculated based on its evaluation at the identity. That then gives rise to the formula that we need. This in particular makes use of permutations and the permutation group. So we prove the standard result here. Let A and B be two n by n matrices of the field K. Then the determinant function is multiplicative. So that can be written as determinant of AB is equal to the product of determinant A times determinant B. We need the given result here first. So let D be an n-linear function on n by n matrices that is alternating. Then D is uniquely determined by its value on the identity and is calculated as the formula gives. So D of A equals D at 1, that is its value at 1, times the product, times the sum over permutations sigma of n letters with the coefficients given as signature of sigma times the product as k goes from 1 to n of ak sigma k. We then recognize or we realize it is also shown that this second sum here, this entire sum, is actually nothing but the determinant evaluated at A. So indeed, now let's begin our proof. We have that alpha j for any given row alpha j can be written as a linear combination of the standard basis vectors ek epsilon k as k goes from 1 to n. The coefficients are given as simply ajk, which is the entry in row j and column k. For other rows fixed now, if we keep other rows apart from alpha j fixed, we know that the function d evaluated at alpha j is the sum with d of epsilon k. So that means in the jth position we are occupying epsilon k. All other rows different from j are as fixed for the matrix A, and we have scalar coefficients of ajk as before. But this procedure cannot stop at just alpha j. It needs to be repeated and completed for all of the other rows of the matrix A from j equals 1 to n. So as we pull out these terms ajk, these coefficients of ajk, as we keep pulling them out for each of the rows of j over the matrix A, what we have is a product as follows. The product is, so it's D of A is given as a product of j going from 1 to n. We've got indices kj with dependence on j going from 1 to n as well. And we've got coefficients of ajk, ajkj. Again, the bounds on j and kj have already been defined, and the determinant is on exactly n rows, all of which are now defined perfectly. No arbitrary figures left. They are epsilon k1, epsilon k2, all the way up to epsilon kn. So these are the standard basis vectors, and they will change as the index kj changes, as each of the indices k1, k2, k3 up to kn change. Now, each of the expressions of d epsilon k1 up to kn is non-zero only when, if and only if, the sequence k1 up to kn consists of n distinct numbers from the list 1 to n. We cannot have any repeats in the indices k1 to kn. But if that were the case, then two particular rows of the matrix epsilon k1 up to epsilon kn would be identical, and since d is alternating, that function would vanish. So we need all of the indices k1 up to kn to be distinct, and cover all of the list 1 to n. Now each sequence corresponds to different permutation sigma of 1 to n. So this is as follows. Now we see that each sequence corresponds to a different permutation sigma of the list 1 to n. We see that every single permutation of the string on n letters will give rise to a different sequence epsilon k1 up to epsilon kn, and that covers the entire sum. So what we essentially have now in essence is the sum over permutations sigma as j goes from 1 to n with a product, and the product is of aj sigma j, because we need to take disjoint entries aj kj such that there is no repeat over rows or over columns, and this permutation sigma ensures that, because sigma is nothing but a bijective function from the list of in numbers to itself, and the remaining standard basis vectors ek1 up to kn are also altered by sigma as it is chosen. That gives epsilon sub sigma. But d of epsilon sub sigma is nothing but sine of sigma times d1, and that's straightforward because we know that the signature of permutation is well defined, and that's exactly how many transpositions are needed to go from the matrix with standard basis vectors in the order of p sub sigma to the identity matrix. That's how many transpositions are needed, and each transposition will give you a factor of -1. So if we need an odd number of transpositions, we multiply by -1, and if we have an even number of transpositions, we multiply by 1. That's exactly what the signature encapsulates. So what we actually see now is that d of e sub sigma can be replaced by signature of sigma times d1, and furthermore, we know that the determinant function is an n-linear alternating function, but it also sends the identity to itself. So if d1 is equal to 1, then we actually have a formula for the determinant, which is nothing but this first sum on the right hand side over here, because the determinant is itself n-linear and it is an alternating function on n by n matrices. So it must be the case that this sum on the right here is nothing but the determinant. And if d is any arbitrary function that does not send the identity to 1, then we will need to account for that by multiplying by d evaluated at 1. That completes the proof for this formula for computing arbitrary n-linear alternating functions, and in particular, most importantly, the determinant function. Now we go back to our proof that the determinant function is multiplicative. So what we do is we define the function d of a very conveniently and very meticulously, or cunningly rather, as the determinant of ab for a fixed matrix B. We prove the given two facts now. So we show that the determinant function d is n-linear. This is very straightforward. So for all rows except for alpha k fixed, if we take a scalar combination of c alpha k plus alpha k prime and evaluate d as that, what we get is the determinant of c alpha k plus alpha k prime times b, and we distribute the product b over addition, as is usually the case. We get c alpha k times b plus alpha k prime times b, and the determinant function is anyways n linear. It's anyways n linear. So it too is going to distribute over the sum and the scalar multiple of C. So we get C times determinant of alpha k b plus determinant of alpha k prime times b. Now, what's important to note is that if, we know that the determinant of alpha k b is nothing but the matrix A with only the vector alpha k in the kth position and all other vectors the same for alpha k prime. So alpha k b can be written as d of alpha k, because that's the particular constraint that we're applying on row k of the matrix A, with all other rows being held fixed. And the second sum here is nothing but d evaluated at alpha k prime, with row k prime being alpha prime k, all other rows being fixed. And the function d was defined to be the determinant of the product of A with B, which is exactly what we have here. This is a product of a row of A with B, and the other rows of A are fixed. They too get multiplied by B. We have just not simply mentioned them in this statement here. Now, the second thing is the function D is alternating. So if two rows of A are equal, then so are two rows of AB, and it follows that determinant AB vanishes. So we know that the function D also vanishes. And now from the previous results for the formula for alternating and linear functions, we have that d of A is equal to d of 1 times the determinant of A. But d of 1 is nothing but the determinant of B, because we have to multiply 1 by B and we get determinant of B. So d of A is equal to determinant of A times determinant of B. And that takes us to the end of this proof that the determinant function is multiplicative. Thank you so much for watching, and please stay tuned for the next video.